In this section, we'll study the QR algorithm or the QR iteration, which is very simple and quite useful. Let's see the QR algorithm. The input is on n by n square metric. We initialize the algorithm A0 equals A, and U0 is the identity metric. In each iteration, we first get the QR factorization of the iterate, and we multiply QR in the opposite way to get a new iterate. And then we update the transformation metric. Each QK is an orthogonal metric, so is UK. Once the algorithm converges, then we'll have the limit of AK and the limit of UK. We'll use the notation T and U to indicate them. We have a claim. The algorithm produces an upper triangle metric T with its diagonals being eigenvalues of A. This claim says that T is upper triangular metric and diagonals are eigenvalues of A. And on orthogonal metric U, such that A is U, T, U transpose. It is called the Schur decomposition of A. When A is symmetric, then T must be symmetric, but T is an upper triangular metric, which means T must be a diagonal metric. Of course, the entries are eigenvalues of A. In this case, U is the collection of corresponding eigenvectors. So when A is symmetric, then we can get eigenvalues and eigenvectors together. But A is a general metric, not symmetric, then we can get only eigenvalues. Here we have a little bit of a theory. Okay. Now, from the algorithm and B and A, we have that. Okay. That is B. AK is RK, QK. And now from A, we multiply QK transpose both sides, then QK transpose AK minus 1 equal RK. So for this RK, we are using that one. These are the same from here. So we reach that equation. Okay. Now we can get this equation recursively as in this equation. Now AK is this one. Now QK transpose QK and AK minus 1. Again, this AK minus 1 is the same as that one, right? And keep going. Then we can reach this term and A0, which is A original one, and then now that is Q1 to QK multiplication, and that is transpose. If we consider this one as UK, of course this is UK in the computation, then this portion will be UK transpose. There's transpose. So here in the limit, we have now T equals U transpose A U. So we get that. Now from here, we multiply u, left hand side, u, and t, then, then u transpose, okay, we are multiplying from left hand side, then there will be identity, and then we multiply it to the right side, u transpose, then u transpose, and then right side must be only a. So we reach at that one. Okay. Here we have an example. We have a matrix A and matrix B. A is not symmetric, but B is symmetric, and we apply QL algorithm to find their Schur decompositions. This is an algorithm, a code for QL iteration. It produces the QL decomposition. So output is now TU and iter, number of iteration inside, so that we want to see how many iterations are carried out, T and U. And once A is symmetric, then U contains eigenvectors of A. Okay, that is initialization for T, and U is the identity metric. And for stopping, we consider the diagonal entries of T, and they're saved in D0, and change. We try to check change along the diagonal entries. In the beginning 1, and tolerance is 10 to the minus 15, and iteration count is 0. Now the loop is organized in this way. While loop, change is larger than tolerance, then we will keep going. But in the beginning is 1, and that is 10 to the minus 5. Now in each iteration for T, we make a QL factorization, and opposite way multiply to get new iterates, and we update the transformation matrix. And then in each iteration, we make a count increased by 1, and then we try to choose the diagonal entries, and then here an earlier diagonal entry and new one, the difference will be measured by using 2 norm, and the result is change. Now this is saved for next iteration, and again once change is larger than the tolerance, then keep going. So that's the QL algorithm. Now we can call it, okay, for matrix A, we call QL algorithm, and we get T1, U1, iteration 1, and here we have the multiplication to check if that makes the original matrix A. Now that one is from built-in function. We try to get an eigenvectors and eigenvalues, and for B, similarly, we do the operations. Now look at here, left hand side, right side is for A and is for B. From QL iteration, QL algorithm, we have here T and U, and then so that these are eigenvalues, and then number of iteration required, performed, is 26. It's a 3 by 3 matrix. It requires 26 iterations. So that you can imagine that once matrix size is very large, then number of iteration is really, really large, which means that the convergence is slow. So there are many acceleration techniques, but those are beyond the scope of the class. If you are in, for example, numerical linear algebra, then you will get information about the acceleration techniques. Okay, this part is now multiplication to check if is correct. And of course, this is A, original A. Now, by using the built-in function, we have here, these are eigenvalues, and these are corresponding eigenvectors. Okay, let's compare with the output from QR iteration. Okay, yeah, diagonals are really eigenvalues. But now these columns are not really eigenvectors, but for this largest eigenvalue, and the first column, that one is negation of that one, so that it looks like right now the first eigenvector is obtained. But except to that, these are not related with any of these eigenvectors, right? How about the symmetric case? For symmetric case, T must be symmetric, so that it must be diagonal. So we have 631, and then U vector, and in claim, it is the claim says that this must be eigenvectors. And number of iterations is 28, again slow. Now that is multiplication U transpose to check if the result is the same as the given metric A. Okay, that's the same. Now by using built-in function EIG, we have eigenvalues and eigenvectors. That is exactly well matching. For 6, this is the eigenvector. Now that is 6. This is the eigenvector. They are the same. For 3, the center one, okay, the same. And for 1 here, the eigenvector, okay, that's the same. Okay, so we checked the claim. The claim is true. Mathematically, we can prove that. Okay. The QR decomposition can also be used for solving least squares problems when the system metric has full rank, and you will solve least squares problems by using QR decomposition. Okay, this is the end of section. Thank you.